Committee of Indian Association of Structural Engineers, IIT Students Chapter, Earthquake Engineering Research Center, IIT Hyderabad. It gives me immense pleasure to share that this is the first event under the banner of IIT Students Chapter of IIT Hyderabad that we are organizing. Today, we have a very eminent personality and an expert in the domain of structural and earthquake engineering, Professor Yogendra Singh. Professor Singh is currently the Railway Bridge Chair and formerly Head of Department of Earthquake Engineering, IIT Roorkee. He obtained his bachelor's degree in civil engineering from IIT Roorkee, formerly the University of Roorkee, in 1989 in first division with honors, and MTech and Ph.D. in structural engineering from IIT Delhi in 1990 and 1994 respectively. His research interest includes performance-based design buildings and bridges, seismic vulnerability and risk evaluation, nonlinear modeling and analysis, seismic evaluation and retrofitting of structures, and earthquake engineering in hilly regions. He has more than 28 years of research and teaching experience, guided more than 14 Ph.Ds, published more than 80 research articles in international journals of repute, and presented more than 100 papers in national and international conferences. He has been a member of several expert teams for post-earthquake damage surveys and is the convener of BIS expert group on performance-based seismic design of structures. He has collaborated with several leading universities and research organizations, including NORSAR-Norway, NGI-Norway, NTU, Singapore, Stanford University, USA, University of Edinburgh, UK, University of Windsor, Canada, University of California, USA, and the University of Porto-Portugal. I now invite Professor Yogendra Singh to deliver his keynote lecture on the topic, Seismic Response Estimation of Structures. Sir, over to you.
Thank you, Mr. Vishwanath Singh. I hope I'm audible.
Yes, sir, you are audible. Yes.
Yes, sir.
So I'm thankful to you to give me this opportunity. Professor Pradeep Kumar, Dr. Parveen Kumar, and I think Dr. Shilpa is still there. So Dr. Shilpa and all the participants who have joined for this afternoon. So thank you very much for coming here. Let me share my screen. I hope you can see my presentation.
Yes, sir.
So as Mr. Vishwanath Singh told you, I'm going to talk about seismic response estimation of structures. So India being a seismic country, most of the region is subjected to quite severe seismic intensity, and no part of the country is free from the earthquakes. So whenever we are designing our structures, earthquake is an essential component of our design. And for designing, we need to estimate the response. So I thought of sharing some of the ideas with you regarding seismic response estimation of structures. Maybe some of you are already into it and have some idea. So we know that earthquake we can record either using an accelegraph, and the record we call accelegram, which is nothing but record of the ground acceleration. So as shown in this top plot, it is record of acceleration due to earthquake. Then we can either record the velocity directly using a seismograph, or we can integrate the acceleration record and get the velocity record, the middle record shown in this figure. And the bottom record, this is integration of the velocity record. It is nothing but displacement. And for us, the engineers, the record of the acceleration, that is accelerogram, is most important, because we are interested in force acting on our structure, and force we can get once we have the ground acceleration. So ground acceleration we can use directly to analyze our structures to get the forces acting on the structures. So this record, if you look at carefully, you will see that the acceleration is changing its direction very rapidly. The whole duration of this earthquake, this is record of El Centro earthquake, one of the quite popular earthquake among the researchers. So the total duration is about 30 seconds. So you can see within 30 seconds how many times it has changed its direction. And we make use of this change in the direction in our design. How? We never design our structures for the actual force which will be applied by this earthquake. Rather, we design our structures for much lower force. And the structure is allowed to deform inelastically, non-linearly. There is a ductility demand on our structure, but it does not collapse. So the structure gets damaged. But what we ensure is that the earthquake, when it's reversing its direction, the structure is not going to collapse in between, and it will be saved by the earthquake force acting in the opposite direction. The other way looking at it is that it is causing vibrations of the ground. It is imparting some energy to our structure, and the structure has to dissipate that energy. So what we have to ensure during earthquake is that the structure can get damaged, but it should not collapse. And collapse of the structure is not indicated by the force demand. It is indicated by the displacement demand. How much displacement is going to occur in my structure? So displacement causes collapse of the structure. The force causes yielding of the structure. But yielding of a structure is not its failure. It's not collapse. The structure can still continue to deform. And once the deformation reaches the ultimate limit, then the structure fails. And when we talk about response estimation, the most important response in which we are interested is the displacement of the structure. Then the second aspect in which we are interested, because all our designs are based on force, so we are also interested in the forces being applied on the structure. So these two aspects we will discuss in today's talk. So first question which comes to our mind is that if I have to design for earthquake, which earthquake I should design for? So here on the screen you see some of the ground motions of some well-known, or I should say notorious earthquakes, which are known due to the damage they have caused. And these are all damaging earthquakes. But if you look at their signatures, this accelerogram, then you see that the accelegrams are very different. In some cases, there are only few cycles, but of very large amplitude. Whereas in case of this Chile earthquake, there is a large number of cycles of moderate intensity. And most interestingly, you look at this Mexico City earthquake, it has very small amplitude. The so-called peak ground acceleration, or PGA, which is the maximum acceleration occurring in the ground, that is quite small. But this also caused a lot of damage in Mexico City. And the reason for that, you can see that it is taking much longer to reverse its direction. So whereas in case of other earthquakes, the acceleration is reverting its direction quite frequently. But here it is taking a lot of time in reversing its direction. And incidentally, this time taken to reverse its direction is also matching with the period of buildings between 5 to 20 stories. And as a result, those buildings were selectively damaged during Mexico City earthquake. So maximum damage was observed in buildings between 5 to 20 stories. The lower buildings were also spared, and the taller buildings, more than 20 stories, those were also spared. So the frequency of the structure, of the earthquake, that also becomes an important parameter. If somehow it is close to the frequency of the structure, the damage will be much larger. So three important characteristics of ground motions have been identified. One is the amplitude of the shaking, the peak ground acceleration, or the peak ground velocity, or the peak ground displacement, because the amplitude is causing the magnitude of the force acting in the structure. So the magnitude of the force depends on the peak ground acceleration. Similarly, the peak ground displacement is resulting in the maximum displacement, which will be called in a flexible structure. So the amplitude is important. Then frequency content, if somehow the frequency content is such that our structure lies within that predominant frequency content of the earthquake, then the damage will be more. And lastly, duration. This is also important because damage is cumulative. And when any structure is subjected to earthquake shaking, every spike you are getting in the acceleration, that is causing some damage. So every cycle is causing some damage to the structure. That damage goes on accumulating, and the accumulated damage will depend on the duration of the earthquake. So duration of earthquake is also important. In most of our analysis, we do not consider the duration. Only in time history analysis, when we perform time history analysis, especially nonlinear time history analysis, then duration comes into picture. But other analysis, we will see the duration does not come into picture, and there we account for the amplitude of the shaking and the frequency content. And these two parameters, the frequency content and amplitude, can be represented by response spectrum. And response spectrum is nothing but a plot of response of single degree freedom system subjected to earthquake. So some of you may be familiar with this single degree freedom system, where we have a mass and either a spring or a single column. It is representing a single story building where mass can be lumped at the top, and the column is representing the stiffness. This column can also represent the damping, or the damping can be represented separately using a dashpot system. And it is subjected to U double dot G. G stands for the ground, and U double dot stands for the second derivative in time. So it is ground acceleration. So when it is subjected to the ground acceleration, the mass undergoes some acceleration, and that acceleration is responsible for the inertia force in the mass. So the force acting on our structure will depend upon U double dot, which in turn depends on U double dot G. But in our design, we are not interested in the inertia force. We are interested in the force acting in our column, because that is the force which will be applicable in the columns or the walls of our building, or for which we have to design our building. So this force which will occur here, which is equal to K into U, U is the displacement. So K into U will be the force. And if we do a little substitution, the maximum value of this force we can write down as the stiffness times the maximum displacement. This maximum displacement we are representing by D, and K we can represent by m omega square. So a little simplification will give us that this force in the column, or the design force, this is m into A, capital A. This capital A, it is also represented by SA, spectral acceleration. This we call pseudo acceleration. Why we call it pseudo acceleration? Because it is not equal to U double dot, which is the actual acceleration of the mass, but it has the units of acceleration, omega square D. So omega is radian per second, radian is dimensionless, so it becomes meter per second square. So it has the same units as that of the acceleration. Its behavior is also similar to acceleration, because when we multiply it by mass, it gives us force, but not the inertia force, but the force acting in the column. And because we are interested in this force and not the inertia force, this pseudo acceleration is more important to us than the real acceleration of the single degree freedom system, U double dot. So we plot this pseudo acceleration for a series of single degree freedom systems with the period of vibration of those single degree freedom systems. So what we get a plot. And this plot is useful to us because if we know the period of our simple structure, that may be a single degree freedom system or a single story building, then we can read the pseudo spectral acceleration directly from here. And that pseudo spectral acceleration, if I multiply by the mass, I will get the force for which I have to design. So this plot we call response spectrum. It can be plotted for pseudo acceleration. It can be plotted for any other response quantity, such as displacement. In that case, it will be called displacement spectrum. It may be for velocity, real velocity or pseudo velocity. Then we can call it velocity spectrum. We can also plot for real acceleration or stress or strain. Any response quantity we can take. And if we plot it with respect to the period of the single degree freedom system, then we call it the response spectrum. So if we plot the response spectrum for a given earthquake, then the shape is something like this. For that earthquake, which I have shown you initially in the first slide, the El Centro earthquake, the variation of the maximum displacement of the single degree freedom system with period is shown here. So you can see it gradually goes on increasing with period. So this is the displacement spectrum for a single earthquake. In the same way, I can plot the pseudo velocity spectrum. Pseudo velocity is nothing but omega times d, and omega, the angular frequency, you may be knowing that it is 2 pi by t, where t is the period of vibration of the single degree freedom system. Then the shape is something like this. It increases, then it attains a more or less constant value, and then it reduces again. In the same manner, we can plot the pseudo acceleration, capital A or SA. Again, it is increasing with period, then it becomes more or less constant, and then it again reduces. What we can see here that for a single earthquake, it is quite zigzag. So this is not a smooth curve, but rather a zigzag variation we get with the period. But if we consider a number of earthquakes and then somehow we normalize those earthquakes, the most common way of normalizing earthquakes is using this ordinate corresponding to 0 period. So this is also called 0 period acceleration or ZPA, or what is given as zone factor in our code is actually this ZPA. So if I take records of earthquakes in different regions, the ZPA corresponding to them will be different. But if I normalize their spectra using this ZPA, then the shape will be close. And if I consider the shape of what is normalized shape of a number of earthquakes, then I can plot the average shape or mean plus 1 sigma shape that will be quite smooth. And the same is given in our code, a shape something like this. And the shape is also affected by the damping. So if I consider different amount of damping in the single degree freedom system, the response will go on reducing. So for 1% damping, you see the top curve, and as the damping goes on increasing up to 20%, you can see that the shape or the ordinate of the normalized shape goes on reducing. What is given in our code is the shape corresponding to 5% damping. So corresponding to 5% damping, the shape is given in our code. Some of you at least might have seen it. It is constant in the initial range, then it reduces proportional to 1 upon t, and then beyond 4 seconds, it becomes constant. And local soil, local site conditions also affect this shape. So what is given in our code are these shapes for 3 types of soil conditions. The type 1, which is rock or hard soil, type 2, the medium soil, and type 3, the soft soil. So you can see for the soft soil, the spectral shape is giving us the maximum order. So the highest spectral acceleration we are getting in case of soft soil, and for hard soil it is the minimum. So as the stiffness of the soil reduces, the spectral acceleration at that soil goes on increasing. Now you see that here this increasing ordinate, which was shown in the response spectrum for single earthquake, is not there. But if you look at the other figure in the code, which code suggests to be taken for response spectrum analysis, there you can see that this increasing arm or the first segment, which goes up to 0.1 second, that is also included. Why it is not included in case of equivalent static method, the response spectrum to be used in case of equivalent static method, it is flat from 0. The reason for that is that most of our structures are having period greater than 0.1 second. And if any structure, even if it is having period less than 0.1 second, suppose it is a very rigid structure, during earthquake, it will invariably crack, it will get damaged. And once it gets damaged, its period increases and it will cross that 0.1 second limit, which we have here. And as a result, it will be subjected to the flat. So we are considering, when we are performing equivalent static method, we are considering this graph flat up to 2.50 period. And when we are considering response spectrum method, means actually a mode superposition method where we are considering number of modes, then the period of the higher modes may be in the range below 0.1 second. And in that case, the code allows to use the reduced responses, reduced spectral acceleration for periods less than 0.1 second. So that's why this range of the response spectrum from 0 period to 0.1 second is also included in this shape, which is to be used for dynamic analysis using response spectrum, or what we call multimodal analysis. Otherwise, both the curves are same. Another issue in our code is that beyond 4 seconds, it takes the spectral acceleration to be constant. This is all right as long as the force calculation is concerned, because the structures having periods greater than 4 seconds, the spectral acceleration value is much less, and those will be subjected to much lower force. So even if we consider this spectral acceleration constant, or the force acting on those structures per unit mass as constant, that is adequate, that can be adequately designed. It doesn't create much problem. But for the flexible structures, the period of vibration being quite long, the displacement, total displacement which will occur in the structure, that may be erroneous, and that will be beyond the practical limits. That's why in the new revision of the code, which is yet to be published, the portion beyond 4 seconds has been modified. It is proportional to 1 upon t square, as it is there in other codes. So if you look at ASC 7 or Eurocode, here you can see that the response spectrum is divided into 5 ranges. So the first range is this range in which it is increasing. Then there is a constant acceleration range. Then there is a constant velocity range. This is proportional to t. And then this portion beyond this period TL, it is proportional to 1 upon t square. SD1 and TL, these are constants. So spectral acceleration is proportional to t square. So in this range, it is proportional to t square, whereas in our code, sorry, proportional to 1 upon t square, or rather inversely proportional to t square. In our code, it is taken constant. And as a result, there is not much problem in spectral acceleration, but when we convert this spectral acceleration into displacement, then we get much higher displacement, which may be difficult to design for in many cases. Now then, another question, related question is, when we are talking about earthquake, that which earthquake or which level of intensity of the earthquake I should design for. So earthquake intensity is indicated in terms of its return period. Similar to what we have in case of floods, we have an average return period. Similar return periods are assigned, average return periods are assigned to earthquakes also. The maximum earthquake which we consider in our design, and we do not want that our building should collapse for that earthquake, is having an average return period of 2,475 years, roughly 2,500 years. So we want that our building which we are designing should not collapse, even if this so-called maximum considered earthquake, or MC, having a return period of 2,500 years. Now, this return period is also expressed in terms of probability of accidents within the lifetime of the structure. Lifetime of the structure here is indicated as 50 years. So the maximum earthquake which we are considering for our design is 2% in 50 years. But we never design for this earthquake. We design actually for this earthquake, which is having a return period of roughly 500 years, 475 years or 500 years. And we call it DB, design basis earthquake. It has a frequency of accidents 10%. So it has 10% probability of being exceeded in 50 years. All the designs are done for this. And it has been seen from the past experience that if we are designing our structures for this level of earthquake with the response reduction factor given in the code, then it will be able to survive MC. Although this is not checked explicitly, but based on experience, we know, the code committee knows, and they have specified that if you are designing for DVE, the structure will be able to survive MC, but not without damage. It will be severely damaged, but it will not collapse, because collapse will mean loss of a lot of lives. So we avoid that. So life loss is avoided, rather large life loss is avoided. Even when we have designed our structure as per code, it will not collapse under MC, but it will be damaging seriously. It will be damaging severely during earthquake. And as a result, it will be causing injury to the occupants, but the fatal injuries should be limited. Then we are not designing our structures for the actual force which is coming during earthquake. We are designing it for reduced force. We are designing it to get damage. Then during earthquake, it will not remain elastic. It will go into inelastic range. So, you know what we call elastic? If the structure is subjected to any loading, and when the loading is removed, it comes back to the original position. That property we call elastic property. And then we have also a term called linear. Linear is mean that the relationship between the force and the displacement is linear. So the force displacement relationship, if it can be represented by a line, or F is equal to K into U, which is representing equation of a line passing from the origin. So that type of behavior we call linear behavior. So whatever you generally study in your graduation, the behavior we are considering there is linear elastic. So the behavior is represented by a line, and at the same time it is also elastic, means it is following loading same path during loading and unloading. So when we unload the structure, it comes back to the original position. But our real structures are not like that. After a particular load, the structure yields, and then it follows a curved load displacement behavior. And finally, at a maximum load, it collapses. So that is the maximum load. And what we do, we represent it by an equivalent bilinear curve by two lines. The initial behavior is represented by an inclined line, and after yielding, we can represent it either by a flat line or a line having a mild slope here, which we call a strain hardening. Or sometimes this slope of the second line may be even negative, a mild negative slope may be here, which we call strain softening. So our structure may behave either in elastoplastic way. Here, this is perfectly plastic, represented by a horizontal line. And if we unload a real structure, let us say represented by elastoplastic behavior, then it does not follow the same path. Rather, it follows a path on unloading like this. This is parallel to the initial loading path. So what we see here, that structure when we load, it yields. After yield, it follows the plastic deformation. And if I unload it from any displacement, then it is not going to follow the loading path. Rather, it will follow another path which is parallel to the loading. And then I start loading again, it will follow another path from the point at which I start loading. It will follow a path parallel to the original loading. So this is the ideal behavior of a elastoplastic structure. And when it is subjected to a cyclic load in both the directions, a reverse cyclic load, then it will be undergoing a hysteretic behavior, and it will have hysteresis. And in this process, it will dissipate energy, and that the energy dissipated in each cycle is equal to the area of the hysteretic loop. So this loop, whatever area is bound by this loop, that much energy it will dissipate in each cycle. And the structure, when it is subjected to earthquake, it is being imparted some energy by the earthquake. The structure should be able to dissipate that energy at the same or higher rate. So when it is able to dissipate that energy at higher rate, it will be able to survive the earthquake. Otherwise, it will collapse. So in case of earthquake resistant design, we try to increase the energy dissipated per cycle as much as possible. And that can be done in two ways. Either I increase this Fy, I increase the strength of the structure, then you can see that the area of the hysteretic loop will increase, or I increase this UN, or what we call ductility. So ductility ratio is defined as the ratio of the ultimate displacement UN, where the structure is failing, to this yield displacement Uy. And you can see this yield displacement is not the displacement corresponding to first yield, where the first member in our structure yielded and our load displacement curve of our structure became nonlinear. It is not that point. It is the point where significant yielding has occurred, and where these two lines in this idealized elastoplastic representation, these are meeting. So this is a notional point actually. And the displacement corresponding to this notional point will represent by yield displacement, and the ratio of UM to UY, this is representing ductility ratio. And hence, ductility is a very important property in earthquake resistant design. The structure is able to survive the earthquake following a combination of strength and ductility. So if my structure is having larger strength, then I don't need larger ductility. And I can increase the area of the hysteretic loop, that is energy dissipated per cycle, even at lower ductility. On the other hand, if the structure is having lower strength, then to dissipate the same amount of energy given by the earthquake, I have to increase the ductility. So the combination of strength and ductility is important. In our conventional analysis, which you might have learned already in your graduation or maybe in post-graduation, we are performing linear analysis. And that gives us the force demand on our structure. We do not perform, usually we do not teach our students the method to calculate ductility until unless you are taking a course on earthquake resistant design. So in earthquake resistant design, we also teach how this ductility can be estimated. So if you look at the response, what effect it has on the response of the single degree freedom system. So here you see this is the response of the single degree freedom system of a given period subjected to El Centro earthquake. So you can see the response is more or less periodic, because during earthquake, the structure is vibrating with its own period. So although the earthquake is causing a forced vibration, but these forced vibrations are such that every cycle of earthquake, every impulse in the earthquake is having different characteristics, and the structure is not able to achieve the steady state. It is vibrating in the transient state only. And you know, in transient state, those who have done some course on dynamics, they know that in the transient state, the structure vibrates with the own frequency. So you can see that it is vibrating with own frequency. The first one is the response of the deformation, and the second one is the response of pseudo acceleration. So what is pseudo acceleration? Force divided by weight. This force is Fs, stiffness force, which is occurring in the column. So whatever force is occurring in the column, if I divide that by W, that gives me a measure of acceleration or pseudo acceleration acting on my structure. So this is the pseudo acceleration. Both are having the same frequency of vibration equal to that of the single degree freedom system. Now here the structure has been subjected to inelastic deformation. How we can subject the structure to inelastic displacement? We do not design it for the elastic force. So in the previous case, the structure was hypothetical. It was designed for very large strength, and as a result, it remained elastic. If I design it for a real strength, the structure will undergo inelastic behavior. And the first plot is that of the displacement. And what you see here, that in displacement, is subjected to some residual displacement. So what you see when the earthquake ends, the structure has a permanent displacement. Whereas as in the previous case, it is not subjected to any permanent displacement. It is vibrating about its initial position. But here there is a permanent displacement. This shows the force which is acting, or the acceleration, and acceleration is nothing but the force divided by weight. So here you see that the acceleration is clipped. and this clipping occurs corresponding to the yield strength of our structure, and yield strength depends upon my design force. So whatever force I have designed my structure for, the structure can resist maximum that much force, and it cannot be subjected to force beyond that. So acceleration has an upper limit, and that upper limit comes from the design of the structure. Whatever force I am designing, maximum force and hence maximum acceleration that can generate my structure is given by that. And what is shown in this lowest figure, this is the duration in which my structure is subjected to inelastic displacement. So wherever this acceleration is clipped, during that period, the structure will be subjected to inelastic displacement, or there will be a ductility demand. So the structure will be subjected to some ductility demand, and if that ductility demand is within the capacity of the structure, then it will be able to survive the earthquake. So these response spectra, which we have plotted earlier for different damping, can also be plotted for different ductility demand. So for example, here, this is for a ductility demand of 1, means our elastic structure. That means the same response spectrum which we have plotted earlier. On the other hand, these spectral accelerations which you see here, these are for the ductility demand of 1.5, 2, 4, and 8. So as the ductility demand on the structure is increasing, the acceleration acting on it, and hence the force acting on it, is decreasing. Or in other words, I can design my structure for reduced forces if the structure can have larger ductility capacity.
Go crazy.
Praveen,
I think there is some loss. Just check.
Can you mute all the participants?
Yeah, I think.
Okay, so you can see that the ductility also has the similar effect as the damping. So damping also results in reduction in the demand on our structure, demand in terms of acceleration, demand in terms of force. The ductility also reduces the force in the same manner. And as the ductility capacity of the structure increases, we can afford to design our structure for much reduced force. And this is taken into account, this advantage is taken in our design through the response reduction factor. So the smoothened response spectra for different ductility are plotted here, similar to damping. So with this background of the earthquake and the structural behavior, we can divide the types of analysis we have available into 4 categories. The first one is the linear static procedure, where we are considering the structure to remain linear, and we do not consider the dynamic nature of the earthquake force. Rather, we represent it by equivalent static method. This is also called single mode analysis. So what is given in our code? The variation of the earthquake force is proportional to h square. It actually means that our first mode we are taking proportional to h square. So it is also called single mode analysis. Here we calculate the base shear, and then that base shear we distribute along the height, and period can be obtained from analysis or even using empirical formula which is given in the code. So we need not to perform any analysis for calculation of earthquake forces here. We can just use the period formula given in the code. We can calculate base shear. We can read spectral acceleration from response spectrum, multiply that by force, and then we distribute that along the height. Okay. Then we can do linear dynamic procedure. Linear dynamic procedure, again, 2 options are possible. One is using response spectrum or mode superposition. The other one is using time history. And again, time history also, 2 possibilities are there. We can do time history analysis of individual modes and then superimpose those, or we can do the time history analysis of the structure as a whole, where we solve the equation of motion of the whole structure using step-by-step integration. But the structure is considered to be linear, even in this case. We are not considering the nonlinear behavior of the structure. Parallel to these, we have two procedures for nonlinear analysis. The first one is nonlinear static procedure, and it is similar to linear static procedure with the difference that here we are considering nonlinear behavior of the structure. So we consider the nonlinear load displacement behavior of our structure, but we consider single mode. And this method is also called pushover analysis. I will explain why we call it pushover analysis. So this is also a single mode method, but here we are considering the nonlinear behavior of the structure. And this is the simplest possible nonlinear analysis of a structure subjected to earthquake. Some people have also tried multi-mode pushover analysis, in which they perform nonlinear static analysis in different modes and then superimpose those. Then we have nonlinear dynamic procedure, and in nonlinear dynamic procedure we can have only nonlinear time history analysis. And here the time history analysis is to be done for the structure as a whole. Some people have tried nonlinear dynamic procedure in different modes or using mode superposition, which they call fast nonlinear time history analysis. But I will show you some of the results. This fast nonlinear time history analysis is approximate. In some cases, it can give acceptable results, but in some cases, the results may be quite erroneous, and we have to be careful in which cases we can use this fast nonlinear analysis. But as the name suggests, fast, it can give us the response very quickly, because here we are not analyzing the full equation of motion. Rather, we are analyzing single degree freedom system, although nonlinear, but corresponding to different modes separately. So in this pushover analysis or nonlinear static analysis, what we have is that the building model is created similar to whatever you have learned for linear analysis. So same model is created, and it is subjected to a lateral force, and the lateral force is distributed along the height in proportion to the fundamental mode. So whatever mode is contributing maximum in this direction of vibration of the building, we take this force proportional to that mode. And the total of this force is represented by the base shear, which is nothing but summation of all these floor loads. And the behavior of the building under this load can be represented by a line, and it will undergo a displacement, which is represented by delta rho. So if I plot a relationship between this base shear and delta rho, I will get a straight line. This is the characteristics of a linear structure. So behavior of a linear model will be resulting in this straight line. Now, this is response of a hypothetical structure, which is very, very strong, stronger than earthquake, but we naturally do not design for that much base shear. We design the earthquake for lower base shear. So what will happen at certain value of base shear? Actually, my structure, some component in my structure will develop a plastic hinge, or it is going to yield. So let us say this member is yielding. How we can get which member is yielding? I can calculate. I can first take an arbitrary value of base shear. I can distribute it along the height with respect to the fundamental mode, and then I can perform an analysis. I will get the applied moment or the demand at different points. I can calculate the capacity at different points, the same points, and the potential locations where the hinges can form. Those are near the joints of the beams and columns, because we know in case of earthquake, the maximum demand, maximum moment occurs near the joints. So when the analysis is performed, I will get the demand. And by knowing the reinforcement and sizes, I will get the capacity. And the demand to capacity ratio I can calculate. And the first hinge will form where the demand to capacity ratio is maximum. So wherever that demand to capacity ratio is maximum, I can equate that demand to capacity ratio equal to 1. And if I do that, I will get the first location of the hinge and the corresponding value of base shear, because I have equated demand to capacity. Suppose I have taken much larger base shear in the beginning than what is required to cause the first plastic hinge, then the demand to capacity ratio will be larger than unity. And in that case, when I'm equating it equal to 1, the base shear will be scaled down so that it corresponds to the first plastic hinge. And once this hinge forms here, for the additional force, for the incremental analysis, this will act as a release. And again, I can perform the analysis and the response will be again given by a straight line, but the slope of this straight line is going to reduce. Why? Because there is a release in the member here. And because of this release, the effective stiffness is going to reduce. So the response of the structure will be again represented by a straight line, but of lower slope. And I can repeat the same procedure, calculating the demand to capacity ratio, equating the maximum demand to capacity ratio equal to 1. I will know the location of the second hinge and the corresponding the base shear and the roof displacement. And I can continue this incremental analysis step by step. The slope of the building will go on, or slope of the base shear versus displacement curve will go on reducing. And it will so happen that at a particular step, the slope will become negative. Why it will become negative? Because of the P delta effects. Because this building is already subjected to gravity load before applying this lateral load. So due to gravity load, as the displacement will increase, the P delta effects will go on increasing. And it may so happen that the stiffness becomes negative at a particular displacement. That means I have to reduce the lateral force rather than increasing it to keep it in equilibrium. And if I keep the force same, the displacement will go on increasing and it will finally collapse. And if I join these segments, linear segments, which I have got between formation of different plastic hinges, this curve is important to us. This curve we call capacity curve. This curve is representing 3 characteristics of the building. One is the stiffness. The initial slope is representing the stiffness. Then the peak value is representing the peak base shear is representing the strength. And then the ultimate to the yield point, that is representing the ratio of ultimate displacement to the yield displacement, that is representing the ductility. So this capacity curve is able to represent stiffness, strength, and ductility of the structure. And that's why we call it characteristic curve or signature of our building. So like that accelerogram or response spectrum was signature of the ground motion. That was the signature of the earthquake. It had no influence of the structure. In the same way, this capacity curve, or what we call pushover curve, this is representative of the building. It has no influence of ground motion. And what we have to do, if I want to estimate the response of my building under a given earthquake, I have to compare the response spectrum and the capacity curve. And this procedure we call capacity spectrum method. So here what we are doing, this is the capacity curve, which we have plotted in the previous slide. And these different points, yellow points which are here, these are representing different steps at which some member is yielding or some member is changing its status, the hinge status. For example, after yield, it will go into immediate occupancy. From immediate occupancy, it will go to life safety. From life safety, it will go to collapse prevention. So that is there. And the last point here, beyond which the capacity curve slope becomes negative or the building becomes unstable, this we call collapse prevention, or the displacement in our structure should be less than the corresponding displacement here. Then only it will be stable. Otherwise, it is going to collapse. So we have to ensure that the response of our structure should be within this. And the response we can obtain using response spectrum. But to be able to use response spectrum, we have to convert our capacity curve also into an equivalent single degree freedom system. Because you recall, the response spectrum is response of the single degree freedom system. Whereas this curve which we have obtained here, this was for the actual multi-story building. So we have to convert this into equivalent single degree freedom system. And how we can obtain this? This base shear which we have here, this base shear we will divide by the mass in the fundamental mode. So, or the weight in the seismic weight in the fundamental mode. And if I divide it by the weight in the fundamental mode, I will get the pseudo acceleration dV by W in terms of G. And if I'm dividing this by mass, I will get pseudo acceleration in terms of meter per second square. Similarly, this roof displacement, that can also be converted into equivalent single degree freedom system, or the displacement of single degree freedom system, by dividing it by gamma 1 into phi 1 roof. This gamma 1 is the modal participation factor for the fundamental mode, and phi 1 roof is the ordinate of the fundamental mode shape at the roof level. So if I divide it by gamma 1 into phi 1 roof, then I will get the displacement of equivalent single degree freedom system. So displacement of equivalent single degree freedom system we represent by SD, spectral displacement. Similarly, the acceleration of equivalent single degree freedom system, BV divided by W1 star, the mass or the weight in the first mode or fundamental mode. Then we can convert this curve into SA versus SD. So we convert our capacity curve also into SA versus SD. We convert our demand, that is the response spectrum, also into SA versus SD. You are familiar in response spectrum SA versus T, where T is the period. But corresponding to T, we can also calculate SD. SD is nothing but SA divided by omega square, or SA into T square by 4 pi square. So if we do that, we will get SD. So both curves are converted into SA versus SD, or what we call ADRS format, acceleration, displacement, response spectrum format. So we convert this into ADRS format, and then we try to see the intersection of these two curves. Now, I told you that the response spectrum which is given in the code is corresponding to 5% demand, and the equivalent damping of our structure goes on increasing as the displacement increases. So what we do, at every point there is a different damping. So we do an iterative process in which we plot the demand curve for different damping, and then we see if it is able to intersect the capacity curve or capacity spectrum at the same value of damping for which this reduced response spectrum is plotted. Then this point represents the response of our structure during earthquake, and this point we also call performance point. So the displacement corresponding to this is the displacement which our structure, the nonlinear structure, inelastic structure, will undergo during earthquake. So this is the simplest method in which we can make use of the same model, provided we are able to calculate the capacity here. So if we can calculate the capacity, the same model, same computer program which we have used for our analysis, usual linear analysis, we can do it. And now several computer softwares are having option for performing this analysis, where you need not to do the bookkeeping when each or particular point is yielding, where the plastic hinge is forming. All that is taken care of by the software itself. Then coming to the nonlinear dynamic analysis, because in static analysis we are considering only fundamental mode, only one mode we have considered. So it is approximate method, and it is valid only for those structures which are having more than 75% mass participation in the fundamental mode. In many structures that is not possible, and other limitation of this equivalent static method is that it is not considering the effect of duration. It does not take into account the accumulation of energy or accumulation of the damage which is occurring in our structure in successive cycles of earthquake, successive impulses of the earthquake. This can be done by using time history analysis, and in time history analysis we select a ground motion. This ground motion is to be selected carefully, and that is one important focus of today's task, today's talk. I will talk about that. And this ground motion, when we apply at the base of the building starts vibrating, and I can get a time record of the roof. So I'm not getting a single value of the displacement, rather I will get a variation of the displacement with time. I can read the maximum displacement from here, and that will give the peak response. Okay. Now this response depends a lot on the input ground motion. So this input ground motion has to be selected very carefully, and the analysis has to be performed for a number of cycles. Number of ground motions. One ground motion is not adequate. So currently AC7 says that when we are performing nonlinear time stay analysis, at least 11 ground motions should be used. Now the advantage of ground motion is that we are taking the full history of the structural behavior into account, and we can go on changing the level of the shaking. That means the intensity of the ground shaking. We can get the behavior of the structure from elastic to inelastic range up to failure. The problem in case of time history analysis, nonlinear time history analysis, is that we have a lot of record-to-record variability. As I said, that the ground motions or the response depends on the selected ground motion. And even if I'm taking different ground motions of same PGA, or even having same spectral acceleration SA corresponding to the fundamental period of the structure, there is a lot of record-to-record variability. So this record-to-record variability is the issue, and that's why we have to select a suite of the ground motion, not a single ground motion. Analysis is not done for single ground motion. Earlier, you were thinking that 3 ground motions are enough, but now AC7, the recent revision in AC7 says that minimum 11 ground motions are to be used. Now these 11 ground motions are to be selected from the past earthquake records, because if we are using artificial ground motions, then there will be a lot of error in the response calculated. So it is suggested that the ground motions should be selected from the database of the past earthquakes. At the end, I will give you some of the links corresponding to different database which are available world over, from where you can select ground motions as per your requirement. And again, you may not be able to get the ground motions, all the ground motions which are matching exactly with your targeted intensity. In that case, you have to perform a scaling. So you can somewhat increase or decrease. Now this scaling has to be limited, because if we use a large scale, for example, if I have a ground motion recorded for a PGA 0.1 G and I want to use it for 0.8 G, so I have to scale it 8 times. That type of scaling will cause a lot of distortion in the ground motion. So the scaling has to be limited, preferably within a factor of 2, but not more than 4. So that type of scaling we can do. And this scaling is to be done in time domain. So you might have seen some of the software, you might have heard that we have a frequency domain scaling also, or what we call spectral matching of the ground motions. But spectral matching of the ground motion alters the characteristics of the ground motion, and that should be avoided. In some cases, that may not be possible because ground motions may not be available at all, satisfying your criteria. In that case, you can go for spectral matching, but generally we should use the ground motions, the recorded ground motions with limited scaling, just multiplying those ground motions by a constant factor, and that factor should be preferably within 2. So 3 types of nonlinear analysis are commonly performed. One is the incremental dynamic analysis. In incremental dynamic analysis, we select one set of the ground motions, anywhere between 11 to several hundreds, it may be there. So commonly when we are designing a building, we are using 11 ground motions. When we are performing fragility analysis of the building, we take minimum 20 to 30 ground motions. So we select a suite of the ground motions, and that suite we scale gradually. So we can start with a smaller scale where we are reducing the intensity, and when we are subjecting our structure to reduce intensity, it will be elastic. So initially its behavior will be elastic. As we will go on increasing the intensity, we will be multiplying with larger and larger factors. Then the structure will go into inelastic range, and we will get a behavior similar to what we have obtained in the pushover analysis. Only difference is that in pushover analysis, we were pushing it under static load. Here we are subjecting it to increasing level of ground motion. The problem with this IDA or incremental dynamic analysis is that we are scaling the same set of the ground motion, and scaling causes distortion. So it is prone to some error. If we want to avoid that, we should select different sets of ground motions corresponding to different levels of intensity. And this method is called multi-stripe analysis. In multi-stripe analysis, we have different sets of ground motions corresponding to different levels of ground shaking. And we are not scaling the same set. So it will require effort in selecting so many sets of the ground motions, but the advantage is that the distortion due to scaling will be minimized. The other type of analysis, the third type of analysis, what we call cloud analysis. Here, this is similar to multi-stripe analysis, but we are not using sets of the ground motions. Rather, we are using one single set of the ground motion, which has intensity distributed in the whole range. So in incremental dynamic analysis, there was one set. In multiple stripe analysis, there were multiple sets, but each set was corresponding to one intensity. Here in cloud analysis, each time history corresponds to different intensity. So there is no clubbing together of the intensity, and that's why it is called cloud analysis. The results of the three are to be interpreted differently. Then we have to perform nonlinear modeling of our structure. In case of nonlinear modeling of the structure for time history analysis, we have to not only specify its capacity in terms of strength and ductility, we have to also specify the full hysteretic behavior. So in ETAPS, there is a model available which we know as fiber hinge. So here in this study, which I'm going to show you, we have calibrated that fiber hinge with experimental data. So it is important that whatever model we are using in nonlinear analysis, the model has to be calibrated with experimental results. For example, in case of a beam, we can use lumped plasticity model. So that lumped plasticity model should be calibrated with cyclic testing results of beams. So in our analysis for the beam, we calibrated lumped plasticity model with the results of the test conducted in our department. In case of columns, because in column PM interaction is to be considered, the lumped plasticity hinge available in ETAPS has some limitations in terms of PM interaction curve. But if we are using fiber hinge model, then that PM interaction curve, PM interaction behavior can also be simulated. And at the same time, we can also simulate the hysteresis. So there are some parameters controlling the behavior in ETAPS. Using those parameters, we can control the hysteretic behavior of our fiber hinge. And here you see we have the calibrated results. So this is the hysteretic curve. The black one is what we have got from the experiment, and the red one is what we have got from the analysis. And here is the energy dissipated with the number of cycles. So you can see that the energy dissipated in analytical model is quite close, and the hysteretic behavior is also quite close to the experimental behavior. Finally, it is the energy dissipated which is important, because as I told you that the energy dissipated per cycle, that decides whether our structure will be able to survive the earthquake or not. So the shape of this hysteresis is very important, and we should try to adjust these factors F, F1, F2, and S in such a way that our numerical model is able to simulate the hysteretic behavior close to the experimental behavior. That is the challenge in this analysis. Okay, and this shows the IDA process. So we select any ground motion. That ground motion we scale with respect to the fundamental period of the structure. So when we scale it, we apply it at the base, and this scaling is simply multiplying the whole time speed by a constant factor, SFI. And this scale ground motion, then we apply at the base, and we get the response, and we plot a displacement, damage measure and the intensity measure. Intensity measure can be spectral acceleration or some other measures I will explain. And the damage measure, this can be either interstory drift or the plastic rotation in the members. Most commonly used is interstory drift. So spectral acceleration SA versus interstory drift. If we plot, we will get a curve similar to the pushover curve. This also we call capacity curve, but dynamic capacity curve. What we are getting in pushover curve, we call it capacity curve or static capacity curve. But what we are getting using time history analysis or incremental dynamic analysis, this we are calling dynamic capacity. There, when the curve was changing its slope, it was representing yield. But here, when the curve is changing its slope and it shows very large increment in the displacement with little increment in the force, that is showing collapse. So here, this point is showing the collapse. Whereas the change in the slope in case of pushover analysis was showing yield. So in multi-scribe analysis, as I said, that we take, let us say, 30 ground motions and perform the analysis of our building to these 30 ground motions. Then we will see that for some of the ground motions, our building is going to collapse. Whereas for other ground motions, it can survive. So we go on performing the analysis for increased intensity, and we go on counting the number of buildings or number of time stages for our building is collapsing. So this gives us, out of the total, these buildings, these ground motions for which the building is collapsing, that gives us the collapse probability. And we can plot this collapse probability with the intensity measure SA. So we will get a curve. This curve we call fragility curve or the vulnerability curve of the structure can be obtained from this. So we can read the probability of collapse of our building from here. The advantage of the ground motions, as I said, is that these are representing the actual condition. The disadvantage is, it's not actually disadvantage, there is some limitation, and that limitation is that we do not get adequate number of ground motion, and in that case we do not have option but to scale the ground motion. Sometimes we can use spectrum compatible or what we call a spectral matched and synthesized accelegrams, but these should be considered, these are considered to be inappropriate only when we do not have any other option. We do not have the ground motions available to us. In that case, we can use this. So I told you how to do the scaling. In scaling, what we do, we take the spectral acceleration corresponding to the fundamental period, and then we multiply the ground motion by a factor in such a way that it is matching with the targeted spectrum here at the fundamental period. Just to show you an example, the left figure shows the original ground motions which we have selected corresponding to a spectral acceleration, and our building was having period corresponding to 1 second. And when we scale it with the spectral acceleration, the shape changes like this. Some of the ground motions are scaled up, some of the ground motions are scaled down, because corresponding to our structure's fundamental period of 1 second, there is a wide range here. So the selected ground motions you will never get, which are satisfying the spectral acceleration which you are looking for. So you have to do the scaling. But what you see here, that these spectral ground motions are matching at this point. But at the other periods, these have quite a large variation. Whereas in our structure, we need the ground motions to satisfy the spectral acceleration in a range. Why? One reason is that we have multiple modes participating in the response of our structure. You know that fundamental mode is having maximum contribution, but actually the higher modes are also contributing. So fundamental mode T1, which is having the longest period among all, and the other modes are having shorter period. So the left side range of the response spectrum from the fundamental period comes into picture because of the higher mode. Then when our structure is yielding, its effective stiffness is reducing. And due to this reduced effective stiffness, its period is elongated. So we have a period shift. So effective period is longer. So we need a range, both sides of the fundamental period, larger than T1 as well as smaller than T1, in which our ground motion should be close to our targeted response spectrum if we want the results to be reliable. Okay, so this can be done using SA average. So this SA average takes into account the shape of the response spectrum in a range, and that range is from 0.2 T or 0.2 T1, representing the fundamental mode, 3 T1. Why 3 T1? Because of the period shift. So the period elongates when the structure gets damaged, it goes into nonlinear range, and 0.2 T1 because higher modes are also contributing, and we should take all modes which are having up to 90% mass participation. And in between, we take these ordinates at an interval of 0.01 second, and we take geometric mean of all these ordinates. And then we use SA average to scale our ground motions in place of SAT1. SAT1 was considering spectral acceleration at one period only. SA average is considering in this range at an interval of 0.01 second, and then it takes the geometric mean of those. And if we use this, then the variability in the response is going to be much small. Now here I have some of the ground motions, some of the websites, sorry, from where you can download the ground motions, and using these, the most important is NGI-2 by University of Berkeley. So most of the earthquake records recorded world over you can find here. Then our department is also maintaining a website where you can find the strong motion recorded within India. So those are available on this. And all these websites are in public domain. These are free. Anybody can download the ground motions here. This NGI-2 also provides you a search engine using which you can select the ground motions corresponding to your targeted response spectrum. So suppose you are selecting ground motions corresponding to MC spectrum. You generate the MC spectrum at your site, give it to NGI-2. It will give you the best fitting ground motions, the ground motions which are having the response spectrum closest to your targeted response spectrum. Those will be provided. Then there are some software tools which you can use for scaling or spectral matching of the ground motions. These are also in public domain. You can download and use those. Okay, Quake Manager is another tool. So this software tool, I have given the PDF file already to Dr. Praveen Kumar. He will share with you. You will find that. The last topic, I will just take 2 more minutes. The last topic I wanted to discuss was the so-called fast nonlinear analysis. So, you know, in linear analysis, we use mode superposition. And using mode superposition, the computational time reduces drastically. The problem with nonlinear time history analysis is that it takes a lot of time. It is a very computationally exhaustive method. It requires a lot of computational effort. It takes a lot of computer time. It is usual to run your structure for weeks, if not for months. For weeks, you have to run your structure to perform the nonlinear time history analysis for a moderate size structure. So people are looking for methods which can be used to obtain the approximate response quickly. And this fast nonlinear analysis is included in ETABS and SAP. And what they do here, although mode superposition is not valid in nonlinear analysis, but they assume that the mode superposition is valid. And they use Ritz vector in place of eigenvector. So in most cases, you will see that the eigenvectors and Ritz vector will give you identical results. But in some cases, Ritz vector can give you better results. So you can try with eigenvectors. Eigenvectors are nothing but the frequencies and mode shapes which you are getting. Those are the eigenvalues and eigenvectors. Similar to those, there is another set of orthogonal vectors which we call as Ritz vector. This takes into account the characteristic of the load, the seismic load. So that's why it has been seen in some cases, Ritz vector results in more accurate response with same number of Ritz modes. Okay, so the building is represented by several nonlinear single degree freedom systems of different period corresponding to different modes. And then the analysis is performed on the single degree freedom set of single degree freedom systems rather than the actual multi-degree freedom model of the structure. And you can see if it is single degree freedom system, analysis will be quite fast and quickly we get the results. So here I have shown the plot of the roof displacement of a building. I do not remember how tall that building was, perhaps 8-story. So that 8-story building, what we are having in this blue color, this is the direct time history analysis or the accurate time history analysis. And what we have from this red dotted lines, this is the fast nonlinear analysis. So, and we have performed analysis under two conditions. The first condition, which was close to yield, the level of inelasticity was low, and the other analysis when the level of inelasticity was large. So you can see that the peak roof displacement in both the cases is quite reasonably estimated. Okay, but if you look at the deformed shape along the height, here I have plotted the interstory drift for the same 8-story building. The blue color, actual or rigorous analysis, and the red color using this fast nonlinear analysis. When the interstory drift is small, okay, you can see that quite reasonable values we get in X and Y direction. When the inelasticity is small. So suppose you want to design a building, you are performing its analysis under DB or MC, then this analysis is quite reasonable. You can, because in the design stage, you will require to perform several analyses, so you can use this fast nonlinear analysis considering the mode superposition. But if we are considering the collapse of the building, then we can see when the building is subjected to large nonlinearity, then you can see in the interstory drift, there can be large difference, what we see here. The roof displacement is more or less same, but the story in which the plastic hinges are taking place, there the change or the difference in the estimated response may be much larger. So it is not really valid at that stage. But if the nonlinearity is limited, then this fast nonlinear analysis is quite useful tool. Very quickly you can go at time history analysis, for which you will require weeks. Here you can get in minutes. So that way it is very useful. So thank you. That's all I wanted to discuss. Different methods for estimating seismic response using the software commonly available in our industry. We can use these methods. Thank you. And if there is any question, I think questions have been recorded by you in question answer, or
yes, sir. We have already recorded few questions. Okay. So yes.
Maybe you can read the questions. I will try to answer.
Sure, sure.
Sir, many thanks for the informative lecture and for covering the different aspects related to seismic loading, methods of linear and nonlinear analysis of structures, and estimation of structures response. Sir, it is really a great experience, great learning experience for all of us. And I see few questions from the participants who are eager to discuss with you. I now request Dr. P. Praveen Kumar Venkatrao, sir, to please read out the questions to Professor Singh.
Thank you, Vishwanath. Sir, we have several questions from the participants. I would like to read one by one.
Okay.
there is a question from Mr. Ahmed. He asks that generally what ductility demand do we use for the concrete building? Is there any quantitative value?
Okay. So there is a simple relationship between the response reduction factor and the ductility demand. Okay. And as per that relationship, R is equal to mu. So response reduction factor is equal to mu. So whatever response reduction factor you are using, that much ductility capacity your structure should have. So that is a simple relationship based on equal displacement, which is valid for buildings having long periods. That means more than 7-story buildings. Usually this will hold good. In buildings having height less than 7 stories, there is another relationship. R is equal to square root 2 mu minus 1. So that can be used to get the relationship between response reduction factor and ductility. So approximately we can calculate ductility demand using that.
So the second question is from the same participant. In capacity curve, what does it mean to be 5% of the total capacity? When we say 5,
being 5% of the total capacity, I am not able to understand. Perhaps what he means is 5% damping.
Damping, yes.
So when we say 5% damping, that means actually even when our structure doesn't go into an elastic range, it has energy dissipation capacity. So elastic structure also dissipates energy, or our structure when in elastic state, it is also dissipating energy, and that characteristic is represented by damping, and the damping is represented as a ratio of critical damping. So when the damping in the structure is 5% of the critical damping, we call it 5% damped response or 5% damped response factor.
Okay, sir. There is a question from Mr. Bharat. He asked that can we compare the results of pushover analysis with the fast nonlinear analysis?
Both have different types of approximations. The fast nonlinear analysis is considering multiple modes, okay, and it is considering time history analysis also, whereas pushover analysis is considering only fundamental mode, and it considers the load or the demand in terms of response spectrum, not in terms of time history.
Right.
Okay, so definitely the fast Fourier, this fast nonlinear analysis is going to give us results more reliable than the pushover analysis, but these will not be as accurate as the full time history analysis.
Okay. Mr. Haider asks that can you explain in a very simple terminology what is fragility analysis?
What is fragility analysis? Okay, so we can obtain response of the structure. I told you that the response is nothing but the displacement, which you can also relate with the damage in the structure. The damage you can relate or you can express in terms of some grade. Okay, so whatever response you are obtaining, that response will be always uncertain. Why it will be uncertain? Because I told you that the record variability, the response depends upon which ground motion I have used. Even if I'm using 11 ground motions, even then, if you are choosing another set of 11 ground motions, their response may be different. So there is uncertainty, there is variability in the response. Then whatever modeling we are doing, that modeling is also approximate. So there will be variation or uncertainty in the response due to our modeling. So if we consider these uncertainties in our analysis, in our estimated response, and those we represent in terms of a log normal distribution, then this is called fragility analysis. I can give you an analogy in terms of limit state design. So we say limit state design is a stochastic method. All of us learned in our graduation. What does that mean as compared to ultimate load method or working stress method? Because here we consider uncertainty in the strength of concrete. If we measure the strength of concrete by testing cubes, and I am testing 100 cubes. Those 100 cubes are going to give me different results.
Right.
So if I want to represent all the possibilities of those 100 cubes, then I plot what we call a normal distribution curve. In the same way, I can perform analysis, and different analysis are going to give me different response. And if I plot a distribution of those responses, it will give me the fragility curve. So that is the fragility analysis. In our normal so-called deterministic analysis, we are getting single response. In fragility analysis, we are getting multiple response. And those responses are distributed. And that distribution is represented by fragility.
Okay, sir. There is a question from Miss Lakshmi. She says, generally under which cases we opt for multi-stripe analysis? Is there any specific situations where
in
we
any
need
case,
to
multi-stripe analysis is better than ideal. So if you can perform, you should go for multi-stripe analysis. If you can, only issue there is that you have to look for so many sets of ground motions. Ground motion sets corresponding to each level of intensity you want to consider in your analysis. So you have to select, you should be able to get so many sets of the ground motion. And generally there are problems in getting ground motion suits corresponding to higher levels of intensity, because so many records of lower intensity have been done in the past, those are available. But the records corresponding to higher intensity are not available. So even if you look at all these sites, websites which I have given you, it will be difficult to select adequate number of ground motion. That's the problem. In that case, we have to go for scaling, and that's IDA, incremental damage.
Mr. Ahmed asks that, let's say there is a 10 to 15 story building, and then I have the option to choose to go for response spectrum analysis, and another is the linear time history analysis. Which one should I go for and why?
In linear method, both the results, or in linear, for linear structure, both the methods gives very close results. So a response spectrum method for our linear analysis and design is good enough. Until unless you are interested in some other quantity in which you are interested in the time variation, then you should go for time history analysis. But usually in our design, we are performing, if we are not going for nonlinear, because in nonlinear analysis, if we want to do dynamic analysis, then response spectrum is not applicable. There we have to go for time history. But in case of linear analysis, response spectrum and time history both are applicable, and we can consider multiple modes even in response spectrum. So it is good enough.
Sir, there is a question related to slide number 43. Can you go to 43?
Slide number 43. Yes.
3 years. The question is why the drift is not maximum at the terrace level and it is maximum somewhere in between. Is there any specific reason for that?
Yeah. See, the drift is maximum at the roof. Okay. First of all, what you are seeing here is not the deformed shape. Please keep in mind. This is interstory drift. So it is not that the deformed shape which will go on. The actual deformation is cumulative of the drift. So whatever drift is the ground story, that will be added to the second story and so on. It is showing the interstory drift. That means the displacement occurring within that story. And that is maximum somewhere in between. Ideally, theoretically, it should have been maximum at the base in the ground story. The reason is that the base shear is maximum, story shear is maximum at the base, so maximum deformation should have occurred here. But practically it does not occur in the first story, it occurs somewhere between first or second story. So that's why maximum we are getting between either story 1 or story 2 somewhere. So this is interstory drift. And the maximum displacement will occur where we are having the maximum story shear. And story shear is not maximum at the top. Story shear is increasing downward. If you accumulate these, if you add these height wise, then you will get deformed shape. So deformation will be maximum at the roof. There is no doubt about that. But it is not representing the deformed shape. It is interstory drift.
Okay, sir. There is a question related to slide number 26, sir, if you can. 26. Yes. Yeah, this is a question from one of the research scholars, Mrs. Niharika. She asked that if the hinged value of the lumped elasticity values are taken from ASC 41, she says that these values are derived from the cyclic experiments. So shall we include this F1 and F2 values as well as in model also?
Actually, for hysteretic model, you need two input. One is the backbone curve. So backbone curve you can got from AC 41. So backbone curve is envelope of that. So envelope of that you can get from AC 41. So whatever values are given in AC 41, those are on conservative side, slightly conservative side as compared to experiment. But those can be safely used. So that will give you the backbone curve. But that doesn't tell you how the loading and unloading will take place. In time history analysis, we need the full hysteresis model. So for that, we need these additional parameters. So these parameters are to be used in addition to what is given in AC 41.
So the another question is, what is the fundamental difference between far field and near field earthquake?
Okay, so far field ground motions are, as the name suggests, close to the epicenter, in the epicentral region, and far field are away from the epicentral region. So near field, close to the epicenter, far field away from the epicenter. And when we are recording the ground motions near to the epicenter, there are some specific characteristics. One such characteristic is what we call a pulse, velocity pulse or fringe. So a fringe is there or a velocity pulse is there. So velocity pulse is nothing but a impulse in our acceleration record, we can say, which has a larger frequency, sorry, which has a smaller frequency, larger period. So as the velocity is the integration of acceleration curve, so because of this large duration, the acceleration is taking in reverting its direction, and when we do the integration, the velocity increases, and as a result the response of the structure will be much larger, although the PGA may be same. So with the same PGA, these ground motions, the near field ground motions having a fling or a velocity pulse, these can cause much larger response of the structure, which many times lead to collapse of the structure. So some collapses have been observed due to this fringe effect. And that's why whenever our building is in near field or our structure is in near field, the code says we have to take caution. We have to consider the special characteristics of the ground motions which can occur in near field.
Okay, sir. We have another question from Mr. Arpan Singh. He asks, what is damage in the structure and how it can be quantified?
Okay. So damage, as we know, it can be seen in many ways. Okay. Actually, it is inability of the structure to perform its originally intended functions. So if there is any compromise in the originally intended function, then it is damage. We can also generally we see it in terms of cracking, crushing, falling of the material. Okay, so we can represent the damage either in qualitative terms, in terms of the crack weight, in terms of how much cracking has occurred, whether the chunks of concrete have fallen, in those terms, or we can represent this in terms of its residual capacity to function. So for example, before yield, a structure has same capability to perform its function as without any deformation. So up till yield, there is no compromise with the originally intended functionality. And at collapse, there is no capacity remaining to perform the original functions. In between, we can grade it. And that grading can be done in many ways. One way is that linearly in terms of the displacement, we can grade it. Let us say we take 0 damage at yield and damage equal to 1 at the ultimate, and in between we can have 0.1, 0.2, 0.3 and so on. Linearly we can interpolate. That is one way. Other way is looking at its cracking and crushing state. So looking at what is the size of the damage, how much interstory drift has taken place, whether there is a permanent drift or not, whether it can come back to the original position or there is a permanent drift. Based on this also, we can define some stages, some limit states of the damage. Okay, so some quantifications of damage are continuous. As I said, the first one, it can be an index. So let us say the plastic displacement at ultimate point is 20 mm. So 0 to 20 mm, I can scale from 0 to 1, and proportionately I can define a damage index 0.1, 0.2, 0.3 in the most simple way. The other may be in terms of IO, LS and CP. So IO is when the cracks are not visible by the naked eye, but yielding has occurred. Life safety is that the cracks are visible. Some falling of material can also take place, but the chunks are fairly small. Those cannot cause injury. So that we define as life safety. Collapse prevention, the chunks are large. There can be injuries. Injuries can also be fatal, but the building is not collapsed. So there can be these qualitative ways of representing damage. There can be quantitative ways of representing damage. And it is still an open area. People are doing research even on this, that how we can quantify damage in most rigorous way, in most reliable way, so that different people, when quantifying the damage, they should come out with the same answer. At the moment, what will happen, different people, when they are doing the response analysis, they can quantify the damage differently. That's the point. So there should be a standard way in which different people are defining the damage in the same manner.
Okay. So the last question of the day is, in seismic design of structures, it is said that the structural member should possess good ductility. And does that really mean that the stiffness should be as less as a stiffer member, which will not undergo any large inelastic deformation?
Okay, so I told you 3 properties when I was talking about the capacity curve. These are 3 properties which are different. I mean, which may not be totally independent, okay, but which are different: stiffness, strength, and ductility. So ductility is a different property than stiffness. A stiffer structure or a stiffer component may be ductile, or a flexible component which may deform a lot, but it may not be ductile. All the deformation is elastic deformation. There is no inelastic deformation. So ductility is representing inelastic deformation. So it is not depending on stiffness directly. Okay, some indirect relationship may be there from the stiffness depending on which material we are using, but it is not directly related with the stiffness. So ductility is a separate property. So we have to check ductility separately, strength separately, and stiffness separately.
Yes, sir. I think all the questions have been answered and they have been properly clarified. So, yes, thank you. Thank you so much, sir. So now I will propose the vote of thanks. Sir, it's really my honor and privilege to propose the vote of thanks on this occasion. On behalf of IIT Student Chapter, IIT Hyderabad, my heartfelt gratitude to you, sir. You spent your busiest time gracing the occasion, and today we really had the opportunity to hear your thoughts on a topic which is of a great interest to the structural engineers, research scholars, and also to the industry people. And in addition to that, I want to extend a very hearty thanks to all the distinguished guests, invitee, faculties, and all the participants for their enormous cooperation. I would like to express my sincere thanks to Professor Pradeep Kumar Ramanchadla, head of the Earthquake Engineering Research Center, for his support and valuable guidance. I am very thankful to the organizing team and their willingness to complete the tasks beyond their comfortable zone was greatly appreciated. I also want to acknowledge my special thanks to the support staff and IT team for their logistic support, help, and assistance. Finally, I want to end this program by extending my sincere gratitude to all of you for being with us in making this event successful. It was indeed a great pleasure. Thank you, one and all. And I would like to share to all the participants that the slides has already been shared by Professor Yogendra Singh. So I will circulate the slide and if possible, the recording of this particular lecture to all the respective participants as well. Thank you.
Yeah, thank you, Professor Yogendra. Thank you very much.
Thank you, Professor Ramachala, and everybody who joined. Thank you. Bye bye. Take care.
Thank you, sir. Thank you so much.